Hello, I'm Dr. Podz, and today I want to explain to you how to find the transfer function of an RC filter. An RC filter is really just a voltage divider with a resistor and a capacitor in series. So the resistor might be on top, the capacitor might be at the bottom, and they are both connected to our input voltage U in. We underline this U in to denote that this is a phasor, it is a complex quantity because we do an AC analysis here. We call the resistor R and the capacitor C. And we are interested in the voltage across the capacitor, which we call UC. Now the transfer function of this filter is defined as the output voltage divided by the input voltage. So G of j omega is the transfer function is UC divided by U in. We can apply the standard voltage divider rule, where we have the impedance of the capacitor divided by the sum of the impedances. The impedance of the resistor is just R, and the impedance of the capacitor again ZC. Now we look up the impedance of a capacitor and we find ZC is equal to 1 over j omega C, where j is the imaginary unit, omega is a frequency, and C is a capacitance of the capacitor. If we insert this in our equation, we get a double fraction. 1 over j omega C in the denominator and R plus 1 over j omega C in the denominator. We can simplify this by multiplying numerator and denominator by j omega C. And then we get a very nice simple equation of 1 over j omega C R plus 1. And that is our result. This is our transfer function for the RC filter. If we look at this function, we can see that it clearly depends on the frequency omega. If we have a low value of omega, say 0, we are applying DC voltage to it, this becomes 1, because the omega disappears and the whole term disappears. So G of naught is 1. DC passes through this filter. On the other hand, if we have a very high frequency and omega goes towards infinity, now this is not a proper notation, but we say we go towards infinity, then we find that the transfer function becomes 0. This means we have a low pass filter, LP for low pass. Low frequencies can pass through and high frequencies can't. But what about if we might be interested in the voltage across the resistor? So if we look at the resistor here and we say we want to calculate the voltage of the resistor. It's getting a bit crowded, so we might want to redraw this. Typically you would put the resistor at the bottom now. So you have the capacitor at the top, resistor at the bottom. Otherwise the circuit is very much the same and the analysis is exactly the same. So we're interested in UR. We apply exactly the same methodology. So we calculate the transfer function G of j omega now as UR divided by U in. So we put the impedance of the resistor at the top, which is R, divided by R plus ZC. Insert the impedance of the capacitor. So we get R divided by R plus 1 over j omega C. And again, we expand with j omega C in order to simplify this equation. And you can see now this multiplies into the numerator and into the denominator. So we get j omega CR in the denominator and j omega CR plus 1 at the bottom of the fraction. And this is our transfer function for the RC filter with the resistor as an output. If we do the same analysis as before, what happens with a very small omega? Then the numerator becomes 0 and we get approximately 1. If we have a very large omega, it would dominate and the 1 becomes unimportant. So if we go to very large frequencies, we can see that these go through. Sorry, just made a mistake there. This is of course a 0. So we can see low frequencies and DC frequencies especially do not pass through this filter. High frequencies do. So this is a high pass filter, HP for high pass. And this is how you can analyze any first order filter. I hope this was useful, and please have a look at the other videos. I will come back to the question of how you analyze a filter with an impedance.